In Chapter 2, we're going to learn how to draw different molecular representations or different ways of drawing organic molecules. The first one you've seen is the Lewis structure, and in the Lewis structure that shows all of the atoms and all of the bonds between the atoms and also the lone pairs. So anytime you draw a Lewis structure, that has to include a lone pair. We also can see next to it the partially condensed structure. So here they take some of the bonds out, so we're not seeing all of the bonds between the hydrogens and the carbons, but just a couple of them there, maybe the important ones. In the condensed structure, it shows these two groups are both CH3s, so they've condensed it and done CH3. We note there's two of them that are bonded to this carbon right here, which is the same as this one, and there's also an OH and a hydrogen bonded to it. So that is the condensed structure. And there's also the molecular formula, which doesn't tell you how the atoms are connected together, just how many carbons, hydrogens, and oxygens. So given that there are 3 isomers of propanol, which structures above are adequate to represent only isopropanol and not its isomers? So this is the structure of isopropanol. We have a CH3, CHOH here, CH3, and then this is propanol. This tells you that there's 3 carbons bonded to the oxygen, and then we have ethyl methyl ether. So the molecular formula here can describe all 3 of these things. So these all have the same molecular formula. They're all constitutional isomers of each other. So the Lewis structure will give you the difference between these 2 compounds, and so will the partially condensed structure and the condensed structure. So the molecular formula is not very good at telling us about different isomers. So if we draw a Lewis structure for the following compound, so we're going to draw each group separately. So if we here, we can see there's 2 CH3s that are bonded to this carbon right here. I'm going to draw this carbon first. So we have C, and there's a CH3 coming off of that, and a CH3. So again, this is the condensed structure. On this carbon also, there's a hydrogen. There's an oxygen with 2 lone pairs. And then the CH2. And then CH3. We have to draw out all of the CH bonds and then include lone pairs. So this is the Lewis version. We can also do a partially condensed. And in that version, we have the CH. Then we can just write CH3, CH3, O, CH2, CH3. So we've eliminated some of those bonds in between all of the carbons and the hydrogens, which condenses it slightly. Go ahead and take a minute to do these Lewis structures for the following compounds. So you're going to draw all the lines and the bonds out. I will draw the answers here and explain it for you in a minute. So I went ahead and drew these out. First, I started with COH. So we have the C, O, and the H here. And then there's 3 of these CH2, CH3 groups. So I have 1 in red, CH2, CH3, 1 in green, CH2, CH3, and then 1 in blue here. For this one, I started with this part of the molecule. We have that C double bond C, the CH2, and then the CH3. And then here we have 2 CH3 groups coming off of this carbon right here. So you can see that in blue and in green. So that's how you would do the Lewis structures for that one. And be sure on the first one here to include those lone pairs because it is a Lewis structure. Your hand maybe got cramped up from writing all those carbons and hydrogens. There is actually a much quicker way to draw organic structures in chemistry. This is the structure of amoxicillin over here. And you can see that it probably took a long time to write that out. I wouldn't make you write that out in the class. But we also have a method called the bond line or the zigzag method, which is much easier to read. It's quicker to draw, and you can quickly identify functional groups. And also it's easy to see the changes in the reactions. This is the way that chemists use to communicate organic structures, so you have to be an expert in drawing these. So this is the Lewis structure of amoxicillin. This is the bond line version. So what you don't see here are all of the carbons drawn out as C's, and we don't see the hydrogens if they're on carbons. So each point here represents a carbon, and then the number of hydrogens that are supposed to be on there are what is inferred. If there's hydrogens on heteroatoms like oxygen or nitrogen, those have to be drawn out. Lines are drawn between atoms to show the covalent bonds, and it also shows the bond angle. So if you have this CH3, CH2, 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 CH3, we have 1, 2, 3, 4, 5, 6 carbons. So you drop your pencil and that starts 1. This is 1, 2, 3, 4, 5, 6. Carbon-hydrogen bonds are omitted, so we don't see any carbon-hydrogen bonds, but a carbon is assumed to be located at every corner or endpoint on the zigzag. The carbon atoms are also not labeled, but if the hydrogen are omitted, how will we know how many H's are attached? For each of these, this point represents a carbon and inferred hydrogens. And we don't show hydrogens. So again, you can determine how many hydrogens based on how many bonds carbon makes. This carbon right here is making a bond to one other carbon. We know that carbon needs to make 4 bonds, so this should have 3 H's on it. This carbon right here is making bonds to 2 other carbons, so there's 2 hydrogens here. So if you had a carbon that was bonded to 3 other carbons, then that would have only 1 hydrogen. So practice identifying the location of, and then count the number of carbon atoms in these structures below. For this first one, we have 1, 2, 3, 4, 5, 6 carbons, so it's C6. This carbon is making a bond to one other, so there's 3 hydrogens here. So 1, 2, 3. This one has 2, 2, 2, 2. This is 1, 2, 3. 3, 6, 7, 8, 9, 10, 11, 12. This has 1, 2, 3, 4, 5, 6. Each of these carbons on the end will have 3. So there's 3. This one has another one. There's 2 here. And 2 here. 3, 6, 9, 10, 11, 12, 13, 14. 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. This one's 14 also. Sorry about that. This has 1, 2, 3, 4, 5, 6, C6, and then there's 3, 6, 9, 12, 13, 14. So if we have double and triple bonds, those are represented using multiple lines. And so if you have a structure like this, it's very hard to see if there's a double bond, at least not quickly. You have to go based on how many bonds are there. So for this first structure, there's a CH2 on the end, and usually if a carbon is singly bonded, it says CH3 on the end. So there's a double bond here. So there's CH2, CH, CH2, CH3. So that's how you would draw that one. So again, there's 2 hydrogens here, 1 here. This is a CH2, this is a CH3. For this one, the double bond is in the middle. So otherwise it would be CH2s if it was just single bonds. So that would be one way to draw it there. And then we have, this is just C's. So these have triple bonds. So that's how you would draw a triple bond carbon, and this one is a triple bond CH, C, CH2, CH3. So we want to draw the triple bond this way to show our bond angles. We do not want to draw our triple bond this way. Bad bond angles. So the C triple bond or SP should be at 180 degrees. Same with that one. That is why we draw the triple bond without zigzagging, because of bond angles. So the zigzags show us the 109.5 degrees, or the 120, or the 180. The drawing that is shown here indicates only 2 bonds connected to this carbon atom, so that's how you can figure out how many hydrogens are. So again, the hydrogen atoms are not shown, but we can assume that there's enough to complete the octet for 4 bonds for each carbon. This structure here actually looks like this if you draw out the hydrogens. So if we try to figure out how many carbon and hydrogen atoms are in the following molecule, this is the structure of Valium. So we'll go through here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So C16. Each of these carbons in this ring are making 3 bonds. There's 1, 2, 3. There's 1 room left for hydrogen. There's 3 here. 2 here. There's none here. This carbon's already making 4 bonds. Same with this one right here. We have 1 here. And 1 here. If we count them up, we should come up with 13 hydrogens. So the formula here is C16H13. Things to remember with the bond line structure. Carbon atoms in a straight chain should be drawn in the zigzag format. So instead of drawing all the carbons and hydrogens out, which takes a long time, just do one of those. So again, if you have 4 carbons here, you drop your pencil and that's when you start counting the 1, 2, 3, 4. And when you draw the double bonds, you want to draw all bonds as far apart as possible. You don't want your double bonds looking like this. So this is bad. And then when drawing single bonds, the direction in which the bonds are drawn is irrelevant. So if you have this structure here, this has 1, 2, 3, 4, 5 carbons. That is the same as this because bonds can rotate around each other. So these two are the same thing. All heteroatoms other than the carbon and hydrogen must also be drawn, and any hydrogen atoms attached to a heteroatom must also be drawn. So if you're going to draw this out, if I look at the main carbon chain, I have 4 carbons. So that's 1, 2, 3, 4, and the OH is on the second carbon. So you wouldn't just draw the O, you have to draw the H in there. And then never draw a carbon with more than 4 bonds. That would be a Texas carbon. This is a Texas carbon. With 5 bonds, this is bad. Do not do. So if we look at some practice problems, there's a couple of different ways to go about it. I think the easiest is to start with what's not in the parentheses. So I have 1, 2, 3, and then an NH2. So 1, 2, 3, and a bond to the NH2. And then in parentheses attached to this carbon right here, which is this one, is 2CH2CH3. So I have 1, 2, and then 1, 2. So that is how you would draw that one. Draw everything except what's in parentheses. So I have CH2, CH, or 1, 2. So there's a double bond, carbon-carbon. Then I have an oxygen. And then there's a CH2, CH. So there's 2 carbons there. So I have the first half of the molecule, and the stuff in parentheses is coming off of this one, and I have 2 CH3 groups. On the zigzag structures, you do not need to draw the lone pairs in, but you can. The next part is identifying functional groups. When you use the bond line, it's very easy to see the difference in functional groups or to see if a reaction has occurred. So if you look at this first reaction here with the H2 platinum, it's hard to see what the difference in the molecules are. But if you show it here, you can see we went from having a double bond to no double bond. So when you have the zigzag format, it makes it a lot easier to see what's happening in the reaction. When certain atoms are bonded together in a specific way and they undergo specific chemical reactions, these are referred to as functional groups. This is the table of functional groups here. The first one, if you have an R group, so R refers to the rest of the molecule. It's kind of like an abbreviation. It's usually a carbon attached to something else. So if you have a carbon next to a halogen where X is chlorine, bromine, or iodine, this is an alkyl halide. When you have a carbon-carbon double bond, this is an alkene. So you can see the examples there in the columns. In a triple bond, this is an alkyne. An OH group is an alcohol. And that needs to have an R group on it, so a carbon there. So water doesn't qualify as an alcohol, and you know that you can't drink water to get drunk. So that is one of the reasons why. So if there's a carbon there, that constitutes an alcohol. An ROR, this is ether. And that one I think of ether bunnies. If you have a bunny, oh bunny. This is an ether bunny. If you have the RSH, this is a thiol. And RSR is a thioether. So it looks kind of like the alcohol and then the ether. They just put the thiol there. And this one here is an aromatic or arene. Thioethers can also be called sulfides. I'll put that here. The ones that you need to be concerned with learning for now are the alkyl halides, alkenes, alkynes, alcohols, and ethers, and then the aromatic. So we'll save the sulfurs for another time. There's more functional groups on this slide. So if you have an R flanked on both sides, carbons here, this is a ketone. If there's an H here instead of an R, that's an aldehyde. This one is an acid halide. This is an acid anhydride or an anhydride. This one is an ester. So all of these have the carbonyls in them. So a C double bond O is a carbonyl. And these all contain the carbonyls, but it's what's on either side of the carbonyl that makes them different. If you have carbons on both sides, it's a ketone. If you have a carbon and a hydrogen, that's an aldehyde. If you have the carbon and the OH, that's a carboxylic acid. Carbon with the halide is an acid halide. Carbon with this O other group here is an anhydride. If you have a carbon with an OR, or this ether here, that's an ester. And a carbon with a nitrogen here, this is an amide. And then this is an amine. All right, so you want to know these. And these. So that may show up on a quiz or exam where you have to identify the functional group. So carbon atoms can have formal charge. The formal charge affects the stability and reactivity of molecules. So you have to be able to identify them if they're present in the bond line representations. So if a carbon has a formal charge, you have to draw the charge in. We can't figure it out based on how many hydrogens are there. So on this structure here, we have a carbon with 3 H's and the electron lone pair. So you can clearly see it's going to have a negative charge because electrons have a negative charge. This one here has the charge, so we know that there's no hydrogen atoms on there. On that carbon right there. And there's 1 hydrogen here. And this one tells us there are 2 H's on that carbon. But if we don't have the formal charge, if this is the same thing and we forgot to write in the formal charge, we would not know. That's why we need to write in the formal charge. Formal charge should always be drawn in. You can leave the lone pairs out because if there is an extra lone pair, then we can infer the charge from that. So this nitrogen, if you don't draw in the lone pairs or the charges, it could be this. So it could have an extra lone pair. It could be short a lone pair and be positively charged, or it could have a radical. So you want to make sure that you include the formal charges on the atoms. If there's a formal charge, then you can figure out from that how many lone pairs are present. To calculate the number of lone pair electrons for an atom, compare the number of valence electrons that should be associated with it and then how many that are actually there. So recall that electrons carry a negative charge. So if you have extra electrons, that should be negative. If you're short electrons, it should be positive. And you're going to look at the valence electrons. For something in row 6, such as oxygen, that should have 6 valence electrons. The Lewis dot structure should have an oxygen with 1, 2, 3, 4, 5, 6. So it should make 2 bonds, 2 electron pairs. There's 0 left over. If there's 1 extra electron pair, then it's negative. If it's short an electron pair, then it's positive. So that's the charge there for that. For nitrogen, which is in the row 5, you have 1, 2, 3, 4, 5. It wants to make 3 bonds, 1 electron pair extra. If there's no extra electrons, the charge is 0. If there's an extra pair of electrons, it's negatively charged. If it's short 1 pair of electrons, then it's positive. Carbon, it likes to make 4 bonds with no electron pairs left over. If there's 0 extra, then there's 0 charge. If there's 1 extra pair of electrons, it's negative. If it's short, then it is positive. So we'll look at this practice problem, so you can go ahead and try to do that. Drawing all the lone pairs in the following structures. You want to use that table from the last slide to see how many are supposed to be there. So this oxygen right here has no electron pairs on it currently, and it has no charge, which means it's neutral, so we should have 2 electron pairs here. If it's a positive charge, it'll be short 1 pair of electrons. If it's a negative charge, it should have 1 extra pair of electrons. And if it's no charge, then it should have 0 extra pairs of electrons. So this one here is short 1 pair. Usually it makes 2, so here it's only going to have 1 pair. If it's negative, it's usually got 2. So for negative, it's going to have 1 extra. So a negatively charged oxygen will have 3 lone pairs. A positive will have 1 pair, and a happy neutral one will have 2 lone pairs. For nitrogen, if it's positive, it's going to be short 1, so it'll have 0, and this one will just have 1 because there's no charge here.